Okay, everybody, I hope everybody hears me well and sees the slides well. My name is Wolfgang Wagner. I'm from the Technical University of Vienna, and I'm very pleased to present you in this webinar today how to use our new HSAF 6.25 kilometer ASCAT soil moisture data for drought monitoring. I would like to start the webinar with some acknowledgements first to my team that you see here. And for this presentation, in particular, thanks for Sebastian Hahn, Mariette Freuchtenhill, Roland Lindorfer, Samuel Massad, Mohamed Hassan, and Pavan Samanjamurti. Yeah, and also thanks for our funding agencies on the international level, EUMETSAT, ESA, the World Bank Group, and on the national scale, so Austrian level, to our ministry, to the Research Funding Agency, and the Austrian Development Agency. Where I'm going to show results from different projects. So let me start first with giving you an introduction to micro-retrieval sensing of soil moisture. I presume many of you already heard about micro-retrieval sensing, and it was already covered in many of the EU Africa seminars. So one of the big advantages of micro-retrieval sensing is that you have all weather day-round measurement capabilities, so we can see through clouds and we can see through rain. All the systems that we're using for measuring soil moisture basically work in the frequency domain from about 1 to 10 gigahertz, and they have absolutely no problem. They also have the fact that these microsystems, they penetrate deeply into vegetation and soil. And the longer wavelengths you have, so the more you penetrate into vegetation, the more you penetrate into the soil. And for the topic of soil moisture retrieval, that's overall beneficial. So if you have L-band data where you have a wavelengths in the order of 20-22 centimeters, you penetrate deeper into vegetation soil, so it's beneficial. And compared, for example, to C-band data from EUMETSAT or ASCAT or Sentinel-1 that have a wavelengths in the order from 5 to 6 centimeter. But as you see here on the graphic here, this shows the dielectric properties of water. So even at C-band, we have a very high dielectric constant of water. That's why we still have a very high sensitivity to the water molecules. Only if you would go beyond the 10 gigahertz range, say 15 or 20 gigahertz, then we would start losing the sensitivity to the water molecules. So these microwave measurements are very sensitive to the dielectric properties related to the water, and also very sensitive to the geometric structure of the surfaces that we are seeing. In micro-retrieval sensing, we have now a different group of sensors that can deliver your soil moisture. Say in the past, we focused mostly on passive micro-retrieval sensing techniques using so-called microwave radiometers that measure the natural radiation emitted by the land surface. So basically, we observe the brightness temperature, which is sensitive to the temperature of the surface, plus the dielectric properties. So we can also derive soil moisture here. And the second group that was the focus on was on radars that send out short microwave pulses and measure the echoes that are received. In the case of radars, what the observable is the so-called radar backscattering coefficient. And also when we use radars, there are different instrument types. The main types are scatterometers, which is the topic of this presentation. And there are also synthetic aperture radars that are very, very important. And the new kid on the block is Global Navigation Satellite Systems Reflectometry, so GNSSR, where we exploit signals of opportunities that are being sent out by GNSS satellites, so signals coming from GPS or Galileo that send out L-band microwaves that are also scattered at the land surface, and we have then passive satellites that receive the forward scattering signals from the GNSS satellites. There the observable is reflectivity. So this technique has come up in the last few years and has become very popular. So I think, well, from now on, basically, it's these three group of sensors that will give us soil moisture retrievals at a global scale. But for this presentation, I would like to focus solely on scatterometers. So scatterometers are side-looking real aperture radars that use antennas to send out short pulses, or so-called chirps. It's, for example, illustrated here. So imagine you have an antenna here installed on an aircraft. These antennas send out short pulses, and because the pulse is very short, so we have achieved a certain ranging resolution here in the range direction. In the direction of propagation of the aircraft or the satellite, we achieve a good spatial resolution by having a long antenna and then having a shorter beam width. In any case, because we have deal here with the technique of real aperture radars, if we implement such techniques on the satellite, the overall resolution or footprint of the measurements is very coarse, in the order of tens of kilometers. But as we will see, the big advantage of those systems is the spatial resolution is coarse, but the temporal resolution is, on the other hand, very, very good. The instrument that we will be looking at is the so-called Advanced Scatterometer installed on the METOP satellite series, where each of those ASCAT instruments has 6 antennas to look on both sides of the satellite track. Yeah, so this is the satellite track, and here you have a left swath and you have a right swath. And each of the left and the right swath is covered by 3 antennas, a mid-beam antenna, a forward-looking antenna, and a backward-looking antenna. And because the satellite moves very quickly, basically each point on the surface is more or less instantaneously measured by 3 different directions, which is very beneficial for our purpose for doing soil moisture retrievals. Now, the Advanced Scatterometer is basically only part of a longer term time series that we have now from European C-band scatterometers. So we started the series with the ERS-1 scatterometer, where ERS-1 was launched in 1991. And we have data until the year 2000, and ERS-2 was launched in 1995, and the data span up to 2011. Now with METOP, we already had 3 satellites. METOP A operated from 2006 to 2021. METOP B was launched in 2012 and still is ongoing, and METOP C was launched in 2018, is also still ongoing. And now we are really looking forward to the next generation of scatterometer missions that will be launched in 2026 with the so-called METOP second generation B1 unit. Yeah, so it seems like it's kind of almost like a law that the naming conventions for satellites becomes more complex over time because there are more and more of these satellites. If we look into the specification of those instruments, we see that we work here at C-band. The frequency is shifting a little bit, say from 5.3 gigahertz for the ERS scatterometer to 5.255 for the ASCAT to 5.3 for the METOP second generation SCA instrument. But this doesn't really matter in terms of our geophysical interpretation. So it's still the same signal. The differences we have is in how radio frequency interference effects impact our measurements. Also, very importantly for our application is that we have always had data in a so-called vertical polarization. So that means we send out electromagnetic waves in vertical polarization and receive vertical polarization back. One novelty of the upcoming SCA instrument is that we will not only have VV, but also VH and HH polarization. So we can do much more interpretation of the data, but it still will be very difficult to initially use those new data sources because, well, we first need to learn how well they're calibrated, what's the data quality, and only from then on we can start actually using them in our retrievals. In terms of the resolution, we have seen a constant improvement in terms of the quality of the data. With the Advanced Scatterometer, we had a spatial resolution in the order of 50 kilometer. Now with ASCAT, we are down to roughly 15 to 25 kilometer, depending on the pre-processing. And with the SCA instrument, we will again double the spatial resolution to about 12.5 kilometer. Also very positive to note is that the daily global coverage improved from below 40% for the Advanced Scatterometer to 82% for now METOP ASCAT for a single satellite, to up to 88% for SCA instrument for only one instrument. If you have more instruments, for example, if you have 2 instruments, then the coverage is much better. You see here the coverage achieved with METOP A and METOP B. You see here there's some white spots here. So basically these are areas not covered by the 2 satellites. It's an unfortunate fact because of the phasing of METOP A and METOP B wasn't favorable for having a complete daily global coverage with the 2 instruments. That was because another instrument had priority over the ASCAT. But once we had a 3rd satellite, actually also these gaps around the equator were pretty much closed. We're also very fortunate that with the upcoming SCA instruments, also these gaps will vanish. So we can be more or less sure that we're going to have daily measurements all around the globe. And for most locations on the Earth, you have measurements twice per day. So during the morning pass and during the evening pass. Yeah, the very good thing about this satellite series is I would say that's the best calibrated remote sensing satellite series that you can get. That's because we can use active transponders for calibrating the satellite signals. And we can also benefit from the fact that, for example, tropical forests can be seen as, say, reference targets. They can be used for cross-calibrating the different satellites. Also, the WINS community, that are the main users of the instrument, they have very good calibration strategies. So we have often observed that even, say, there's a change of 0.1 dB in the signal, that the WINS community immediately cries out saying, oh, the winds are too slow or they are too fast. So there was really very reliable detection of any drifts that we've seen in the data. And accordingly, if you now put the backscatter measurements for METOP A, METOP B, and METOP C on top of each other, you see that all the instruments are extremely well calibrated. Now let me introduce the surface soil moisture data that are being derived from the backscatter measurements. Yeah, the main product we're deriving is like a product that has been started as in terms of operations by EUMETSAT. So there was a near real-time workflow that was run at EUMETSAT, and that started in 2008. And since that time, it has been running uninterrupted. Formally, that service was integrated into the satellite application facility in support to hydrology in 2015. As a user, you didn't notice this. The specification of that particular product came mostly from the meteorological community, who said they wanted to have soil moisture data as close as possible to the satellite measurements. They also made the very important requirement that the data must be as near real time as possible, meaning within 3 hours after sensing. So you can imagine that the METOP satellites keep on cycling the Earth's surface all the time, and data are being dumped in northern latitudes to receiving station in Svalbard. From there, they directly go to Darmstadt in Germany, where the data are being processed. Soil moisture is also processed. The data are then redirected to the satellite network, and within 2 to 3 hours, users around the world can receive the data. The data represented in degree of saturation, so an index between 0 and 1. Yeah, and we had 2 resolution products, one with a sampling of 12.5 kilometer and one with 25 kilometer. up to now. The product is not just also deriving just soil moisture, but it also provides mass and quality flex. Yeah, in a way, it's our most important product because there are a couple of downstream products, like for example, a soil water index product that is being delivered by the Copernicus Land Monitoring Service. And also this product goes into the climate change initiative data from the European Space Agency or into the climate change service of Copernicus. The algorithm that we use for deriving soil moisture from the backscatter measurements is a change detection algorithm, where we try to describe the impact of seasonal vegetation growth on the data, so that we correct it. And we basically scale the measurements between very, very dry soil conditions and very wet soil conditions. So this graphic illustrates if you, for example, we observe a certain maximum measurements, say around -9 dB, and we see minimum measurements during the dry season with low vegetation around -15 dB. Then a measurement around -12 dB would be medium wet conditions. If now vegetation is growing, then backscatter typically goes up, reflecting vegetation growth. Then the sensitivity to the measurement, to the soil moisture decreases. So the measurements become somewhat more uncertain. But because we have a rather high quality of the data, we still can derive soil moisture also during the height of the season. The development of the product has a long history. So I started this research in the 90s, and the algorithms were basically published in 1999. And within the next 3 years, we then deployed the algorithms and make them run on a global scale. And we were quite happy with the results, and first users came in to check the quality of the data. So that at some point in time, the EUMETSAT decided to make the product operationally. So we basically took the algorithm from the Advanced Scatterometer, adopted it to ASCAT, and from then on, this service was running. Based on this base product, we also derived then higher value datasets, like for example, the ESA CCI dataset. And once the product was running, we spent a lot of time on error characterization. So we tried to understand the errors as good as possible before we started to actually improving the algorithm. So it really took us many, many years to understand different error influences on the product, so that we then finally went into model refinements and a new way of calibrating the data. And now I'm very happy to say that after so many years of research, it is in this year that we bring out a new product that contains many new algorithmic improvements. So this update that we have in this year is certainly the biggest update since the start of near real-time operations in the year 2008. So the basic characteristics of the products are still the same, but there will be now a different gridding system and spatial resolution on a different fixed earth grid. So the new fixed earth grid is now a Fibonacci grid, a grid representation that is, for example, also used by the European Center for Medium Range Weather Forecasting. We start the whole processing also from a more raw data sets than we did in the past. So this has made it possible that we now move to a grid of 6.25 kilometers. Please let me also highlight here that there's a difference between spatial sampling and spatial resolution. When I call the product here 6.25 kilometer, I refer to the sampling of the product, so in which spacing the grid points are on the Earth's surface. The actual resolution, so the footprint of the data, is more closer to 15 kilometers. There's also a certain product that is going to be used by the Met services that work at 12.5 kilometer sampling, and that has then a resolution of 25 kilometer. And the difference of this is here you have a higher spatial resolution with a bit more uncertainty or noise, and here you have a coarser resolution with reduced noise. Yeah, here on the bottom you see the two grids shown for the case of Italy. Yeah, so obviously if we go to the 6.12 kilometer sampling, we come closer to the coastline, for example, and we resolve more spatial features. Yeah, and this slide included all the updates that we have done to the product. I'm not going to go through it, but I will share after this presentation the slides, and then you can see as a summary of all these changes that are coming. I only want to focus on two aspects that have been very well challenging to really find out, and that have a big impact on how you interpret the data, particularly over Africa, and particularly for the case of drought monitoring. The first algorithmic improvement that we applied here was accounting for the fact that we observed that the backscatter measurements acquired by the scatterometers seem to have increased over many parts of the world. Yeah, so for example, here you see a graphic that illustrates in areas that are shown in green, where we have seen long-term changes in backscatter. So basically higher backscatter. There are some areas that here shown by these pinkish colors where we saw a decrease. Now the challenge is now some of these backscatter changes could of course reflect real changes in the climate, so meaning higher soil moisture conditions, or maybe meaning also more vegetation. But there certainly can also be land cover changes that have an impact on the trend. Yeah, so in order to reliably estimate then the real soil moisture changes, we had to remove the land cover effects. I just show you now two examples of like extreme land cover changes. Yeah, possibly the pixels that have been affected most are cities that have grown over the last years that are situated in desert environments. Yeah, for example, if you looked at Dubai or Abu Dhabi, and if you look at the backscatter time series over individual locations, you observed for all these changes from 2007 up to 2020, we observed a steady increase of backscatter that basically reflects the increasing building environment within the footprint of the satellite. So obviously it didn't get wetter in the area, we just saw that there are more buildings, so we had to adopt our algorithms in such a way that the model parameterization was adapted to more dynamically reflect those land cover changes. So that in the end, we at least reduce very much this long-term trend. So this is the case of Abu Dhabi, a similar case here for China, where this is an area where we've seen many more like a sprawl of urban environments. Yeah, like if we then also looked into Africa, we've observed it's not necessarily just urban environments, urban sprawl that can cause these changes, but it can also be vegetation, long-term vegetation changes that push backscatter up and down. Yeah, so an easy case would be, if example, if you have an area where forests is cut down over very large areas, obviously backscatter could go down. But we have also observed the case that if you have a series of wet years, then there could be such vigorous vegetation growth in an area, so that for us it constituted more or less land cover change because the biomass in the area has changed a lot. So we also had to account for this. So by having now the new algorithm, we basically have trends in the data that are much less pronounced than in the older version and much better in line with reference data, as for example from ERA 5 or Childers. So that was the first very important improvement. A second topic that's of very high relevance in Africa is the problem of subsurface scattering. In the introduction of the talk, I told you that if you have longer wavelengths, it's beneficial because I can penetrate better through vegetation and soil. Now, this high penetration into soil can also be a disadvantage because let us look here at the left case. Imagine that you have rock below a layer of soil. If you think of a desert area, there could be a layer of sand. The backscatter here from the sand isn't particularly strong because the sand is typically smooth. The sand is typically dry, so backscatter actually from the sandy surface is very low. But backscatter from the rock below could be extremely strong, giving you a dominating signal at the satellite. If now let's say there's a rainfall event and the soil layer intermediate is wetting, what will happen is that backscatter from the top here increases, pushing up backscatter a little bit as expected. On the other side, what happens is that the signals coming from the rock below are dampened because the microwaves are being absorbed by the layer of water that is contained in the soil. So if you're in extreme conditions, it could happen that the reduction of the signals from the rock is the much more important influence than the increase from the top. So that in areas where we have such dominant subsurface scattering, that backscatter could decrease with increasing soil moisture conditions. That's totally opposite to all physical models that we are having that says backscatter should actually go up if soil moisture increases. Now, most of the world shows dominant surface scattering. A few areas in desert areas show dominant subsurface scatterers. But there's also areas where these two things mix. We call them mixed scattering areas. So that during dry conditions, you have initially a decrease in backscatter with increasing soil moisture until you reach a certain minimum level, and then it goes up. The problem now for us is, at the moment, we're only assuming that the scattering behavior follows this dominant surface scatterers. So we cannot properly account for dominant subsurface scatterers, and so far we cannot yet account for mixed scattering phenomena. That causes them problem. Let me give you two examples. Here is an area that is situated within Saudi Arabia. That is more or less a dominant subsurface scattering area. You see, for example, here in blue, model soil moisture data from the NOAA Childers dataset, so the American data assimilation dataset, where you have here a series of rainfall events that is wettening the soil. And if you look now here at the backscatter measurements done by the Advanced Scatterometer, it's like almost a direct inversion of the signal from the soil surface. So here you see exactly this inverse relationship between soil moisture and backscatter. A more challenging area is, for example, here in the Sahel zone in Mali. If you are during the wet season, and what you see here in the graph is the blue line shows you precipitation, the turquoise color here shows you ERA 5 land soil moisture, so modeled soil moisture data. The pink one here is the ASCAT backscatter data, and the gray one line here is the vegetation index. Yeah, you see that during the rainfall season, backscatter nicely follows the peaks, the rainfall peaks. So every time there's rainfall, backscatter goes up, and then there's a certain drying. So this is typical chainsaw behavior. We also see here, when we look at the vegetation behavior, that the signal is typically responding to the soil moisture conditions, and only with time, the vegetation signal is also causing backscatter to increase a little bit. But that's something we then correct within our procedure. What's for our purpose is more interesting is now this phenomenon, that when I come into the dry season, that I see now the soil has really dried out, and I don't see any signal now any longer in the model soil moisture data, but I see a certain increase in backscatter in the ASCAT measurements. And once there's a significant rainfall, I see a drop in backscatter. So what's exactly happening here is that during the very dry season, I'm here at the very dry edge. After the first rainfall, it may happen that I end up here at this point. And only from this point onward, it goes up again. So for a very long time, we have been very confused about what happened with the backscatter signals in the Sahel zone, for example, but now we understand what's going on. Unfortunately, we cannot yet account for it. So we either mask for it, or you basically, maybe for some of the applications, actually the problem is not that severe. Typically, defects are not that strong. So this is a point that is where the signal is actually very strong. There are other points where it's not that strong. Anyhow, we have now been looking for the subsurface scattering signals, and we have mapped them on a global scale. You can also do this dynamically. And if you, for example, look at the month of March, then we see subsurface scattering to occur in those areas here. So the darker the color is, the more robust subsurface scattering signals we are observing. So in March, most of, say, the intertropical convergence zone is still in the process of moving upwards. So here it's still wet. So as long as wet, I don't see subsurface scattering. But here it's still dry, so I see subsurface scattering phenomena. And once the intertropical convergence zone has moved to its northernward position in August, it basically takes away all subsurface scattering effects, leaving those effects just over to the desert areas. So here we nicely see this, this phenomena that during the dry season, I may have problems. During the wet season, I typically have very good signals. So we hope now that we are getting a project to actually account for those phenomena, so that we integrate into our algorithm a way of how to account for the subsurface scattering effects. At the moment, it's not yet accounted. So what we do is we are now providing masks that allows you to mask those areas. And these are the areas here in orange. And they will be changing depending on the season. Again, this is just like masks. You can apply, or you do not need to apply it. So you can test a little bit for your applications if it's critical or not. Yeah, in any case, once we've done all the new changes, not those two I just discussed, and if you do a comparison against passive microwave-derived soil moisture data or against a model soil moisture data set, you see here then we get rather good correlations against those independent reference data. So for most areas, we get very strong correlations, in particular in areas where we have the high variability of the soil moisture signals. Obviously, if we go into desert areas where we believe we can do soil moisture retrievals, deserts are still typically dry almost all year round, so correlations per se cannot be very high. So, and how can you access those HSAF ASCAT soil moisture data? I show you here the link to the HSAF website, where you can then go to the product section. There's snow products, there's precipitation products, and there's a range of different soil moisture products where then you can access those data. Yeah, and if you want to have tools for working the data, at our website of our department, we have a couple of Python code, so toolboxes that are free for use. For example, you see here like a software package that's called ASCAT that helps you to read and visualize the data from the ASCAT. There's also tools, for example, here Pythesno, the Python toolbox for the evaluation of soil moisture observations. And here's also a toolbox for reading in data from in situ data from the International Soil Moisture Network. So please check them out if you work with Python. Okay, now let us assume you have read in successfully the data, and now you want to start interpreting them. So the first thing you can do is to, for example, compute soil moisture anomalies in different ways. Let me, this is not bad. Okay, I don't see this. It should be an animation. Okay, I jumped direct. What I wanted to illustrate here, on the left side, you see soil moisture data derived from Sentinel-1. So not from ASCAT, but from Sentinel-1. And you see here rather dry conditions for most of the area, except an area here that is wetted up. What on the right-hand side should have been shown is an animation that shows a rainfall cloud moving over the area, leaving an imprint of rainfall on the surface here on that location. So the soil moisture measurements are very good like measure of where rainfall reached the ground. I've first seen Chris Taylor participating in this webinar. He recently showed me his very nice website. He's looking into the relationship between soil moisture conditions and precipitation clouds. It's a very nice website where I give you here the link where you can compare rainfall estimates with soil moisture anomalies. So for example, here the blue colors here is where the soil has been wetted and observed by ASCAT, and here these greenish colors and red colors show where rainfall is at a certain point in time. Obviously, the rainfall clouds move more fast. With ASCAT, we only have like measurements in the morning and in the evening, so it doesn't capture all this dynamics that is there in the rainfall, but it's still at 2 times a day, it tells you where rainfall had an impact on the soil moisture conditions. So this is a zoom in, and you can also get like a large scale overview combining, for example, the ascending and descending orbits from ASCAT. Let me also point to the very nice work from colleagues around Luca Bocca from Italy, who had the idea to use the soil moisture data to actually estimate how much rain has come. Yeah, normally you take rainfall data to estimate how much soil moisture is there on the surface. But actually, why not turn this relationship around? So normally you describe changes in soil moisture over time are related to how much precipitation there is, minus runoff, minus evapotranspiration, minus drainage. Obviously, you can turn it around, that is, say precipitation becomes the first derivative of soil moisture over time, plus those terms here. If you make some assumptions there, then within a short time frame, these are either set to 0 or can be approximated with a certain assumption. Then you find that precipitation amount can be estimated by looking at the changes in soil moisture conditions over time. That's a very nice algorithm. Again, this should be an animation. These are now the so-called SM2Rain datasets that become increasingly available, not just for ASCAT, but now also for Sentinel-1, or SMOS or SMAP and other satellite data. And we see that these are very valuable because they have different error structures, very complementary to other rainfall data sets, either observed on the ground or with other satellite methods. Okay, so this was focusing on short-term soil moisture anomalies that very much reflect the input from precipitation. Now, if you start aggregating surface soil moisture observations over a longer time period, for example, say a month, then these become indicative of extreme weather conditions. Yeah, for example, here we did anomalies for the months of July 2021 and soil moisture anomalies for the months of July 2022. Yeah, so obviously wet conditions might indicate that there was flooding or other problems related to too much water. And if it's dry, it can mean it was a drought situation. Yeah, indeed, for example, in July 2021, there was a very serious flooding in Germany, in Belgium here. Yeah, that was really disastrous. On next year, we basically had a drought in Europe. The same here. There was a very serious drought in China in July 2022, and extreme wet conditions leading to flooding here in India and Pakistan. And now you can obviously do these kind of anomaly plots for many, many years. This shows you, for example, soil moisture anomalies for the month of July for the different years from 2007 to 2014. On the top panel, you see the anomalies shown from ASCAT, and on the bottom row, you see those from ERA 5. Yeah, when you compare the two panels, you see that typically from the scatterometer, anomalies are a bit more pronounced. We also see more spatial features compared to the model data. Yeah, so sometimes obviously the features seen in the satellite data can also be related to some errors in the data. Yeah, can happen. But in many cases, I also would believe that actually they can capture the spatial heterogeneity of the signals better than what models can, because the models are very much dependent on the density of the in situ data in the representation of soil moisture patterns. So here we see the years 2007 to 2014, and here we go from 15 to 2022. So here you already start to have a feeling on how we can capture changes from year to year with the ASCAT data. But just being able to compute anomalies doesn't mean that you actually can use the data for drought monitoring. So you need to do additional steps there. Yeah, let us remember that there's different types of drought. There is meteorological drought, where we have precipitation deficiency. Meteorological drought could also mean that there's high temperature leading to increased evapotranspiration. Even though you can now, I would even argue, well, that always part of a so-called agricultural drought, but basically plants don't get enough soil water any longer, so to experience plant water stress. So meteorological drought comes first, agricultural drought comes typically later. Hydrological droughts even takes longer time to take effect, so that means reduced stream flows in major rivers or smaller rivers. It could mean that reservoirs or small lakes are drying out. And last but not least, all these effects may finally start propagating, affecting our society. So there could then become really socioeconomic drought scenarios that leading to food insecurity, or it could even lead to conflict and violence in case conditions are really very bad. This obviously is, say, for example, very worsened if there's drought conditions for multiple years after each other. If you look at this more from a process understanding, and if you have many variables to characterize your drought conditions, it could, for example, you look not just for soil moisture, but you look at precipitation, you look at evaporation, you look into vegetation conditions, you look into temperature. You basically see a propagation of drought conditions in these variables. So you first see it in like a precipitation deficit. You might see it as an increase in temperature. Then you see a reduction in surface soil moisture conditions. After that, you see a reduction in deeper layer soil moisture conditions, so in the root zone. And finally, it propagates down to the vegetation. There's a certain time lag related to those processes, and that again depends on the climate. Say, the warmer and the more energy there is in a certain climatic environment, the faster this process can go. So in Africa, those processes would be typically very fast, while if you would go to Europe, where there's not so much energy, these are typically slower, those processes. Now that was a bit theoretical. Let me show you two examples that illustrate the point. Here on the upper panels, you see the case of Eastern Europe, Romania, Ukraine. There was a serious drought in the year 2007 in July, indicated here by the below soil moisture conditions. And if we then looked into vegetation conditions at the beginning of August, we saw how very nicely the soil moisture deficit seen here is then being reflected in the vegetation conditions. To show that it can actually be also in exactly the opposite behavior is shown here in the lower panel. We see here soil moisture conditions for March 2008 and April 2008 in India. We see extreme wet conditions leading then to extreme positive vegetation anomalies on the for southern India. This delayed response of vegetation to soil moisture anomalies can then be used in modeling efforts. Imagine that you have a monitoring system where you monitor vegetation using the normalized difference vegetation index. So you could use NDVI observations, and you can use soil water index, so like the ASCAT soil moisture observations. And what you could do is maybe to predict the next month NDVI using the current month NDVI and soil water index from ASCAT. So it's a way of predicting potential drought impact. And that was a very nice study done by a team of French scientists around Mechas-Ribri, who did this for Tunisia. And you see here the observed satellite vegetation time series in black. And the red line shows you the predicted NDVI with this approach. It's calibrated for each point, but once you have time series, actually it's not a big deal for doing this, in particular now with the many machine learning tools that are around there. Now let me also address the topic of drought indicators. If you look nowadays into the literature, there's dozens of drought indicators that all kind of express the deficit of soil moisture with respect to the expected conditions. Yeah, so here I refer to a paper by my colleague Mariette Röchtenhill, who published in Frontiers. So again, she did a review of different indicators. This is not even a complete list. And again, they always kind of depend a bit on how they're exactly calculated, how they are normalized, and also very importantly, how thresholds are set for different indicators. Yeah, so different ways of calculating anomalies leads to different ways of how we set thresholds. And yeah, we can now take these different methods, we can implement it. you can set up workflows. What in all the cases you need to do is you need to get historical soil moisture data. You need to process them to characterize kind of the expected soil moisture conditions. So you need to have climate data records, and then you can start comparing the near real-time data with the climate data records. I would like to refer here to a very nice report written by our colleague Muhammad Hassan, who did associate scientist study for the EUMETSAT H stuff, where he shows how to develop workflows for climate, normal and anomaly calculations for satellite soil moisture products. Yeah, so again, I recommend going to that report that is also provided here on ResearchGate. Yeah, so that you, for example, would have two different ways of calculating anomalies. Here, an index code with SMA, here an index code with SMAPI. Here you would show, well, wet conditions and dry conditions. Wet conditions indicated by those blue areas, dry conditions by those red areas. You see here, there's a bit of differences in the dynamics between the two products, but basically, if it's wet, it's wet. If it's dry. Maybe the biggest difference from my point of view is how different indicators classify droughts. Yeah, SMAPI would have then, for example, key thresholds where, say, if soil moisture is below the average, you very quickly call it mild drought, quickly going over to moderate drought, then to severe drought, and then to extreme drought. So if you now compare different drought indices, you see here a couple of them, so from Z-score, here SMAPI, yeah, so all of them, as I said, a bit calculated with difference, looking at current conditions with respect to the climate normals. You see that patterns deviate a bit, where the biggest change between those indicators is of how they finally classify the anomaly, if they call it then severe drought or extreme drought. Yeah, for example, here you would see, for example, that SMAPI is one that shows severe drought conditions, while others say, well, or extreme drought conditions, while others say, well, it's pretty bad drought. We call it severe or even moderate. So that's the difference. So I think when you apply those drought indices, it's also about learning how to interpret them, how to relate them, what's happening to the field. In one of our recent projects, we have done this exercise in particular for countries situated in Eastern Africa. You see those countries here. And we've developed a dashboard where we showed 3 different drought indicators based on the ASCAT data, based on SMAPI, Z-score, and SMA. We also represented the data in terms of monthly data and decadal data. We also have like some display of food insecurity level or data from an international disaster database. So you can select the date. For example, this is the year 2012, the month December. Yeah, so the month of December 2028. And then you can click on one point, and for example, here for that point, you would show for the Z-score, how it changes over years. Yeah, this was just a research project, so it's more or less a demonstrator dashboard, so we don't have any near real-time data in there. If you would be curious how it looks for near real-time data, at the moment we have a project running in Mozambique, where we also implemented those chains to actually display the data in quasi near real time. If, for example, look at the current conditions in Mozambique, we would find that the southern parts of Mozambique all find they're actually pretty wet. Yeah, for example, look here that in situ data that we're also collecting in Mozambique, we would find that, yeah, there has been quite some rain recently, so no problems. Only in the northern parts of Mozambique, there are some areas that are below average wet conditions. We're trying in this project to work together with local partners to achieve an adoption at local scale and a long-term sustainability. So that brings me to my last slide, and almost perfect in the hour. So let me wrap up by saying that with the European seabed scatterometers, the very good thing about scatterometers is we know that we're going to have the data also in the future. So it really sets these data type apart from data like, for example, coming from SMOS or SMEP, where basically after SMOS and SMEP, there will be no continuation. And those scatterometers are extremely well calibrated. Yeah, the other important feature is this new ASCAT soil measure data stream is coming very, very soon. So in May or June, it should be ready. It basically now waits for the official approval by the EUMETSAT HSAF. And again, it's the most important algorithmic update. So in case you have worked still with the old data, please expect there's going to be a major change to the product, so that you need to adopt your processing algorithms and procedures to the new data set. Unfortunately, the new ASCAT, the current ASCAT data flow will stop already in June, so the transition time from now to June will not be very long. If you work with drought monitoring, then you need in particular long time series. So for the data going back to 2007, they are readily available for ASCAT. You can also go back even to 1992 if you also use data from the ERS scatterometer, but then you need to make compromises on the spatial resolution. So it's not that fine resolution, but it's more coarser, but then the benefit would be that you can go back in time. And maybe as a last statement is, obviously, drought research still needs to be done. We still need to learn a lot on how you can assign the observations to real drought classes. And we need to understand how all these observations relate to drought impacts at local and national scale. And you will always need local and national scale data to actually understand and make this link. So that there's always local expertise required to make meaningful, to make the data meaningful. And maybe also let me make the two statements. One issue is how to deal with multi-year drought conditions. With most of the methods, we're just looking at current conditions with respect to long-term average, but obviously if you have a series of years where we have drought conditions, that makes things worse, but it's very difficult to describe. And last but not least, there's many variables that indicate drought conditions. So you also want to look at precipitation, vegetation, temperature. So how to best combine all this drought information into one indicator and to relate things happening to the ground. Also there's already different combinations of indices, but I'm sure things can be improved there. Yeah, with this, I would like to thank you for your attention. I hope you could hear me well and you saw the slides well. I'm sorry for the technical issues, and I'm now happy to answer your questions. I will stop with my presentation because otherwise I won't see you and I won't see the questions in the chat. Okay, I see there's already many questions here. Thank you for comments. Ooh. Okay, so many messages relate the same one. Yeah, now I see a question: how close to the coastline can one be confident on the 6.25 kilometer resolution? I would say look at the data. As a first guess, if you say 10 kilometers away from the coastline, you should be on the safe side, but it depends on the exact shape of the coastline. In any case, the open water surface has a very big impact on the soil moisture observations. So if you have a point that is still impacted by an open water surface, you will see signals that don't make sense. Yeah, so, but again, as a rule of thumb, if you're 10 kilometers away, I think you can use it. There's new messages. Yes, ASCAT data are simulated in the Era 5, but not in the Era 5 land. And I think I've shown the Era 5 land data. Okay, there's a Q&A section as well. There was one question: how to evaluate the capacity of drought indices based on soil moisture data. I would say the evaluation of the effectiveness of different drought indices is always very difficult. It's also very difficult for drought indices based on precipitation data, on vegetation data. I think it's more a matter of existing know-how. People are used to work with standardized precipitation index data for different monthly periods. Many people are used to work with drought indicators based on vegetation anomalies. So I think it also will take time and availability of the soil moisture data for you to start working with it. Overall, as a scientist, I always find many drought studies in a way critical because it's hard to quantify how good they are, because we often have so little information from the ground on the real impacts, so that it's hard to say which indicator is best. I see another question: which polarization can we use with Sentinel-1A to map rock and stone subsurface? Yeah, we have also implemented the methods for detecting subsurface scattering for Sentinel-1, and we've used VV polarization. We also did a little bit of experiments with VH. If you're using cross polarization, there are subsurface scattering effects, because often it's a volume scattering effect. It can be even seen in the VH data itself. Yeah, so you can use it. It gives you a very nice local scale patterns, informing us where like rocks and stones are very close to the surface. And we've seen cases where, for example, if you have an agricultural field where we've seen normal soil conditions, and then you went to the next field that, for example, was an olive haim, where olive trees are growing, and their soils were much poorer, and then you saw subsurface scattering effects. Then I see another question. We need to address impacts at local to national scale. Given the core spatial resolution, What could be its impact on relating soil moisture conditions on vegetation conditions at local scales? Yeah, so this is a question that often comes. If you ask people, most would say, well, I would like to have soil moisture conditions at field scale or even better. I fully understand this, and if you want to do precision agriculture, you obviously would need to have soil moisture variability within a field. There's also now people doing this kind of products by merging different data sets from optical data and radar data, doing some machine learning, getting some patterns out of it. I'm not particularly sure if this always shows soil moisture. I think it often more shows, like, I don't know, topography or vegetation conditions. Let me start with this statement. On the other side, one feature of soil moisture is very favorable to actually use data from different spatial scale to characterize phenomena on a local scale. Yeah, say if you look at soil moisture, you can imagine it's driven at the large scale by precipitation and evapotranspiration. So that means soil moisture in many cases has some autocorrelation over longer distances. And what we see in the Advanced Scatterometer data, or what you see in SMOS and SMAP, reflects often, if you look in the time domain, very much the time domain happening on a local scale. So there's this phenomenon is also referred to as temporal stability, that we basically see regional patterns reflected on a local scale. Obviously, it's not magic. There can be points locally that don't reflect those regional trends. For example, imagine you have a point close to a river that's always wet. It doesn't reflect the regional environment. But still, I believe coarse resolution satellite data are even very beneficial to describe things on a more local scale, knowing that one point might be typically wetter than another one, and another point may be typically drier. But this is something, information that you can integrate with local knowledge in, and you use the information about the temporal dynamics from the satellite data. Yeah, here's a question: why most of the available soil moisture products have coarse spatial resolution? It's a trade-off. When you make a satellite sensor, you always have technical trade-offs. Imagining it like this, you could say, I would like to have a 1 meter image every day. Building such a satellite system is not possible, at least not with one satellite. You either use the energy that the satellite has to give you high resolution images, but then you can cover only smaller areas, or you say, well, I don't care so much about the spatial resolution as I accept a coarser resolution, and then you can cover a much larger area per day. So there's always a trade-off between the spatial versus the temporal resolution. And the higher the spatial resolution becomes, the coarser or the longer it takes before the satellite comes back again. And if you look now at the phenomena of soil moisture, I think it's extremely important to have very frequent observations, because soil moisture changes if there's rainfall. So if you imagine, for example, you would only have measurements every week. Say you have one measurement on Sunday, the next measurement in comes next Sunday. But the rainfall that comes on Tuesday or Wednesday is never seen, because on Sunday it's already gone. So I think it's extremely important to capture the dynamics. Yeah, and so that I think most satellite systems are designed in such a way to capture these dynamics, saying it's more important than to understand really on a smaller scale. But obviously, many people are now working on combining the coarse resolution satellite products with other satellite sources or modeling approaches to downscale and come to a final resolution. So, let's say the latest generation of products that typically try to go to a 1 kilometer scale, trying this with, say, a sampling interval of daily to several days. I think there we're still very much at the beginning. Many products that are out there show you some spatial patterns, but we don't know yet how good those spatial patterns are. So very clearly, those coarse resolution products from SMES, SMEP, SMOS, ASCAT, EUMETSAT, or fused data sets of those like the CCI are at the moment the more mature, more reliable data sets that you can have. The 1 kilometer products are more experimental. And if you go to even finer resolution, I think you need to be very, very careful to actually how to interpret the data if it's not vegetation that you're seeing rather than so much. Now I'll switch back to the chat to see if there's another one. Yeah, there's one question. If you go to higher latitudes, we have better coverage in the day. Yes, that's true. The best coverage is the more you go to the north or the more you go to the south, the coverage is getting better. Well, and if you go, for example, to Siberia, it can be that you have 6 or 8 acquisitions per day. Like one group of measurements around the morning orbits and the other group of measurements in the evening. Yeah, so for mid-latitudes, like for example, Europe, in most of the days we have 2 measurements per day. If you're in Africa, I would say with 2 satellites, also with ASCAT, you typically will have 2 measurements per day, but not as often as over Europe, for example. Okay, I don't see any new question coming in. Here again in the chat. The question is if there could be if there's an alternative to validate the downscale soil moisture data, referring to FLDAS in data scale regions where there's no in situ data. Yeah, it's really difficult to say. The validation of higher sample soil moisture data is really difficult, in particular in areas where you don't have in situ data. Yeah, obviously. I mean, luckily, there's also progress in the way how modeling, say, models are realized. So I also have started to have more and more confidence in models that, for example, are implemented at 1 kilometer scale. Also now there's efforts, for example, in Europe as part of the Destination Earth initiative to go down from the modeling side from the 10-kilometer grid to a 1-kilometer grid, giving you a more realistic representation of rainfall, leading to improved estimation of local soil conditions. But obviously, also there, it's just starting. So that's an active area of research to find out how we can best analyze the high resolution soil moisture data. I believe we are still very much at the beginning, and that we often still apply the methods that we have developed for the coarse resolution data, while it's a way of practically dealing with the current situation, but certainly we need new methods, we need new data, we need new approaches for understanding the quality of the spatial signals. Here's a question about temporal spatial resolution for small islands in the Caribbean. If the island is too small to, then we can't, unfortunately, from the ASCAT not derive information. You could, for example, look at Sentinel-1 data for doing monitoring over the smaller islands. Again, there's a big but. Most of these islands are not often covered by SAR sensors, but say only a few weeks or even every few months. So it's not very useful for doing soil moisture estimation. So for many of smaller islands, I guess, yeah, unfortunately, there's not good data at the moment yet. Or is it possible to use pre-trained model? If you refer to a model as a physical model, or do you refer to a model, for example, machine learning? I've seen more and more people also training machine learning methods, trying to predict soil moisture using, for example, precipitation input data and machine learning models trained for a certain reference data set. Yeah, I mean, first results are very interesting. Could be an approach, but again, I think we need to learn much more on how robust machine learning models are, in particular if you transfer them from one region to the next. Very often the problem in machine learning is that the machine learning models are overtrained. So you use too many parameters, the machine learning model is too complex, so that the transfer from one region to the next is extremely problematic. The same could be said of physical models, but there I guess the problem is less pronounced, because with the physical model you can at least check the plausibility of some of the parameterization. So it might not be that wrong, but also validating it is often very difficult. In many cases, if people apply models and you look at the data, and the data, for example, show you that soil moisture kind of reflects the topographic patterns, or if it reflects vegetation patterns, that gives you kind of confidence that you believe you do something correctly. But again, that could only be reflecting our expectation while not reflecting the real situation on the ground. Yeah, I'm not sure if some of you know, but I'm also recently posting a couple of things on LinkedIn. And sometimes I post something a bit more critical about machine learning, because many people are extremely enthusiastic about machine learning. And I mean, and it's fantastic. It can do a lot of things, but sometimes we tend to lose our critical view on the things, and it becomes particularly problematic if you do things with machine learning that goes beyond the physical limits of what data can tell you. So again, be careful of not to overtune the machine learning algorithms, be careful of not over-interpreting the results, but always keep in mind which are the data that go in and what is information that really can come out of the data.